Okay, so before we start, I haven't yet reached the ballistic FET that I've asked you in the assignment, which is the topic also for this class today. So, and I think I'll have to extend the deadline for the assignment to Thursday, I think next week. So can spend a little more time, but and next Friday we don't have any extra classes. I think next Friday. But anyway, okay. So I'll send out an email about that, and in this email I'll also send out a list of kind of suggested research topics that you for your projects, and you can start thinking about it. We are about a month, slightly more than a month into the semester, and I want all of you to select a topic by the prelims that we'll have somewhere in the middle of the semester. We have only one prelim in this class, and then after that it's your project time. So you pick, start working on your projects. Okay. And because I think is next Friday a holiday? I don't even know. Fall break? No, it's not. So I may not be around next Friday, but I'll have another set of office hours next week before the assignment is due. So you can, if you want, get that. Okay. So let's see. We were looking at. So we have looked in the last class. We looked at the one-dimensional ballistic transport and also one-dimensional scattering limited transport. We saw what is mobility, conductivity as is defined in scattering limited transport, and we saw what is conductivity as defined in completely ballistic transport, which we saw that conductance for one dimension or conductivity, if you might, in one dimension, the same thing was given by for spin of 2 2q squared by the Planck's constant. So that's something we saw fell out very simply from looking at electron transport as through a set of wave modes through allowed states, right? So that's something that came out, and when we allow scattering, the conductance is always lower than this. So this is kind of the max we can get through a single one-dimensional mode. Okay? And now we are going to higher dimensions, and at the same time, what I'm trying to introduce is kind of the idea that whatever we have done till now it's clearly applicable in vacuum, for example, or things like that. But once you put it in a solid, then clearly things are changing, right? And for that, we discussed that when we put particles in a solid, we have this periodic potential, and it's kind of every solid state physics course. This is what you cover. That if you have a periodic potential, the electron cannot have. This is the potential energy profile that the electron is seeing. It's a generic potential. This is a cosine potential, but in general you have much more complicated ones where near the nuclei it might go to very large lower energies. Regardless, so in a free electron state, the band structure allowed electron states are this parabolic dispersion, momentum squared by twice free electron mass. That's the kinetic energy, right, in a free electron case. And whenever we have a periodicity of A, we have periodic potential with a real space periodicity of A, then we have this characteristic k values which are given by pi over A and minus pi over A. So at those k values, the wavelength of the electron matches up with the wavelength of the periodic potential, and you get standing wave formation, right? So that's the idea. And these energies, all these energies were allowed. So if you consider it as a band, all the energies were allowed. But once you have this periodic potential, because of standing wave formation, there's a set of energies that is not allowed anymore, and those electrons, if you try to inject them at that energy, it will get reflected back. That's the physical meaning, that the electron at that energy is not an allowed state in the system. So very similar to when light is incident on a metal, it reflected back, very similar in principle. So, it's not allowed, but and this energy gap is very much related to what is the strength of this potential, right? You can see that if you turn the potential, the strength of this amplitude of this cosine wave to 0, you've gone back to free electrons, right? So the gap will close, right? So the gap is related to the strength of the potential, and it's, if you have a perfectly periodic cosine function like that, then it is just the amplitude of the crest to trough to UG. It's exactly that, and actually that's 4 times, but it's related. I mean, it's linearly proportional to that. So yeah. So this we get from physics, and then now we fill in electrons. These are all the allowed states, and we put in electrons into the system. And if I have only one electron, then it can occupy some state here. But then I fill in, every atom that's sitting here. Every atom comes with a certain number of electrons. For typical semiconductors like silicon, or each atom comes with many electrons. Many of them form core levels that are deep inside, that don't even form chemical bond to the next atom. The ones that form the chemical bonds are the outermost shells of the atoms, right? And those outermost shell, so in silicon, for example, there are 4, right? 1 s and 3 p orbitals that will chemically bond to the next atom. Those electrons are shared. And for those electrons, we are looking at only when the electrons are shared between atoms, they can actually have a momentum. So there's only those electrons have a band structure. Does that make sense? I mean, all the other electrons are localized. They are bound states for the atom. They are not moving, so they don't have. We're not drawing their band structure at all. The EK diagrams that we are sketching are only for the outermost shell electrons. And among them, in silicon, for example, there will be 2 more of these. So there will be 2 more bands. So let me put it this way. So there will be multiple bands like this, then multiple gaps, based on the number of electrons. If I fill it up, and I run out of electrons at this point, then this is my fundamental band gap, and this is conduction band, and that's the valence band. So that's a very simple picture of all semiconductors. Later on, we'll see that, for certain classes of material, the topological insulators, it can change slightly, but on the whole, this is correct. I mean, whatever I said, this is very general, and it's correct. And if a Fermi level is somewhere inside a band, then it's a metal, and if it's filled, that's a semiconductor. Now we are looking at transport, and we're looking at, instead of free electron band like that, we generally, what we do is we try to plot everything in the first Brillouin zone, because because of a wave, it being a wave, a k plus 2 pi and a k. If you translate something by 2 pi along the x-axis, or you translate something by the reciprocal lattice vector, which is g, by the x-axis. So these things are actually, because the potential is periodic. If potential is periodic, and you're solving for electron states, right? So basically, what you're solving is the Schrodinger equation all over again for the periodic potential, right? That's in V of x, such that V of x plus a is equal to V of x. I mean, that's really what you're solving. You're finding what are the allowed energies if I have a periodic potential, right? And then essentially what this solution is telling you is the allowed energies are given by that picture, the band structure. Those are the allowed eigenvalues. And it's different for different k's. You have allowed different energies for different k's. And just like individual atoms, Actually, there's a very close analogy to individual atoms in the periodic table. You know, if you're looking at electrons in a periodic table, you have hydrogen that has one electron, and so that is extremely reactive. You know, it will try to bond to anything that wants to give away or take an electron. I mean, it can form hydrogen chloride, hydrogen fluoride, all that stuff. It will chemically bond, right? When you go to the next atom, helium. Now that s orbital is full, it has one up and one down electron, so it's extremely inert. Right? It doesn't want to react with anything, right? You go to the next, sodium, it has one extra electron. Now it again is very reactive, right? So there's this periodic nature of going between insulating, very reactive, insulating. I mean, that's also the name periodic table, right? In a very similar way, once you have a crystal, it's the same thing, except we're now talking about conductivity. You know, if I increase the number of electrons, as you can see, I have multiple bands. If I increase the number of electrons, and let's say I fill up a band, it's insulated now. You put a little more, now you have metal, right? An insulator and metal and all that. Now that happens obviously from this picture. I mean, if you move from the left side of the periodic table, you have metals. Move towards the middle, you have semiconductors, right? And then you have gas form. It's not even a solid. You know, gas is separate. But then you have this sort of periodicity also in the periodic table because of this, right?
Yeah. Saying with that point, you were saying like valence. You have a valence band layered by conductance band layered by valence band.
Yeah. So what I'm saying is when you solve this, let's say for silicon or whatever. I mean, what we have now is for atoms we had individual energies, right? Yeah. And now I form a crystal, right? And we have already seen from a very simple sort of tight binding picture that if the electrons can bond to other electrons, then let's say this electron can bond to the next one, right? Then it will form a band, right? We have seen that, right? And let's say, you know, it forms a band something like this, and we can, if it can bond, then it will have some momentum k. If it cannot bond, there's no, you know, there's a bound state. There's no k for that. So this band, you know, this energy state, maybe it came from a pz orbital or whatever. It became a band. This one also became a band. That became a band, right? So now you have multiple bands of states that were initially atomic states, and then you have spread out, and because of it being in a crystal, it's become a band. So what I'm trying to say now is based on how many electrons are there per atom that participate in this bonding. You know, you can go from metal to semiconductor to metal to insulator to metal to insulator, and you go through periodic table again. Just so you start with sodium, magnesium, and all that, and you reach carbon, and then you come back to the next. So you're filling up electrons as you go with you start with sodium. Maybe you have something like this. The Fermi level is here, right? 1 electron per atom, right? You increase, you go to magnesium, it's a little bit higher. You go to higher and higher, and then finally you reach, in the first row of the periodic table, you reach carbon, which is diamond, right? And then now you have maybe filled up the whole thing now. So you reach a semiconductor now, and you have a gap. That's all I'm saying. So this shows up because it's in a crystal, in a condensed matter state or a solid state. It shows up as a transport problem now instead of chemical reactivity. Does that make sense? I'm trying to draw an analogy between chemical reactivity and electrical transport. And actually there is a strong analogy because they are both related to electrons, right? And they are both related to how many electrons are available for doing that business. I mean, that physical phenomena. Chemical reactivity would be to form chemical bonds. Here it would be the electron for it to be able to move through the crystal, right? And you can see why it will go through period cycles of being very easy to move through a crystal, then being very hard, then very easy, very hard, and so on. Right? So that's something intrinsic. Okay. Yeah, is that fine? All right. So now the basic picture we are now saying is we are going to fill it up, and our semiconductor model would be: I filled up this band, and that band is empty, and I have a certain gap, and now all my transport will occur either in the conduction band here or in this valence band here, very close to the band gap of the material. So that's a semiconductor. If we're talking about metals, then the Fermi level is inside here. Okay, and now So if I zoom into this point here, E of k, if I'm going to look primarily at the conduction band, and we're going to focus on that a bit today, we look at the conduction band, and I zoom in here, then and I draw the band structure E versus k all over again, and you can see now that the minimum is what I'm labeling as E sub c. This is the conduction band edge, the minimum of the conduction. E sub c and is the minimum of the conduction band, minimum energy, and all the other states allowed above it near any minimum is a parabola, and this parabola is, the formula for that parabola is EC plus h square, k square by twice the effective mass of the conduction band, the curvature. This is just a number, right? And it's clearly not, it is not equal to the free electron mass, because it has come from the fact that there is a periodic potential like this, right? And it is related to how strong is the potential, etc., etc. It is really not related to effective mass, not the free electron mass. And what you can prove is that for the conduction band, if your band is shaped this way, curving downwards, this is going to be smaller than the free electron mass. You can prove that. It's going to be lighter. It's going to behave as if it's, it's not like the electron has become lighter, but because it's in a solid, if you want to draw a classical analogy, if you, there may be, so it's kind of periodically accelerating, decelerating, accelerating, decelerating, but when you integrate, it's actually moving faster because, so that's one analogy. In fact, that's actually a pretty apt analogy that, maybe I'm just thinking. So if I had a ball rolling along this direction and another rolling along this direction, the question may be which one will reach here first in classical physics, and you can show it this one will reach there first, because it will probably accelerate, decelerate, and all that due to whatever gravitational forces or whatever. So there is some analogy to it, but I don't want to draw any of that analogy. I'm just saying it is lighter because it is going through these periodic cycles of acceleration and deceleration, and acceleration means the velocity went up, and deceleration it came back to its original state. So on the average, the velocity was larger, if you want to think of it that way. But it's not. I'm not saying it's quantitative. I'm just saying if you want some analogies. But then by the same token, the holes are actually, you can prove that if you have a valence band, the holes, it depends. Sometimes it can be larger if you have a valence band which curves down. Sometimes it can be larger than free electron mass. Sometimes it can be smaller than free electron. It depends for holes. The conduction band, you can prove it. But regardless, at this point, I'm just saying that it's different, and this has been also written up in the notes I have given you on the chapter of electron, band gaps and effective masses and all that stuff. So you can please read that up. Okay? But I'm going to use this now to look at the idea of the quantum transfer through solids, and I just give you a little more formal or rather introduction to this. The fact that effective mass appears here can also be derived completely from the Schrödinger equation itself. And this was done by Luttinger and Walter Kohn, so Nobel Prize winner. He also led to DFT, development of DFT and all that. But anyway, so they are here's the basic idea of that paper. It's a little dense, but here's the basic idea of that paper. What it says is the following: that if I put electrons in a periodic potential like what we had just talked about, if this potential is periodic, then each of these states is eigenstate, and Bloch, Felix Bloch had already given us a formula for that state. Mathematically, it looks like e to the power ikx times a periodic function in x, uk of x. It's something like this. Okay. Physically, it's very easy to see why one should have that situation. If my potential is periodic, right, and if this is periodic, then you can see that if I take mod psi squared, that's the probability of finding the electron, right, at x, that has to be periodic too. Right? I mean, intuitively, there's no other option, right? I mean, if potential is periodic, then whatever electron distribution you have has to be periodic because, by symmetry itself, right? There's no other option. So if psi x squared is periodic, then clearly x plus a is equal to psi of x, right, squared, right? And I can take away these and say that, if I have the situation that psi of x plus a is equal to some e to the power I times a certain phase times psi of x, then I am good. I mean, that will give me that relation, right? So you will always get this situation. I mean, this will satisfy this physical symmetry condition, right? And you can also see that if if my crystal was of a length L and I had n lattice sites, 1, 2, 3 and so on, I had n lattice sites, and I go, you can see here, if I go translate x by a, I get a phase phi, let's say, right? If I translate by 2a, I must get e to the power I 2 phi, right? Just by repeated application of this same thing, right? And if I translate it by n times a, I should get just big N times phi. That's what I should get, n times psi of x. But if it's a periodic crystal, that thing is the same as this one, right? You have come back to yourself, right? Periodic crystal means come back to yourself. So that means this thing must be equal to 1, right? That you know that, and you get an information about the phase too from here, right? That this phase is not any phase. It depends, it knows about the fact that you are in a periodic crystal too, right? It's not any random phase. And here n times this phi must be equal to some integer times, pi, 2 pi, right? That's very clear, right? It must be like that. And so these phi's are not all values are allowed, but these are also quantized. This angles phase phi's are also quantized, and the phi happens to be this over big N, right? So basically what you're doing, this is the derivation of the Bloch theorem. You can also kind of derive it or say that here's the reason for it. And if I multiply now both by the lattice constant, a on top and the bottom times n times a, so n times a is just the length of the crystal 2 pi by big L, right? Right? And you can see that this is basically what is integer, small integer times n. That's essentially x sub n. This is the lattice point, right? X sub n, right? And this, so I'm just trying to say why do you have a e to the power I kx? This is where it comes from. This is effectively, you can think of as k and x, in that sense. And all n's from 0 all the way to n minus 1, they're all allowed. And these are all your k points, 0, 1, 2, these are all the k points here, right? And your wave function, from here you can show it's a Bloch function. I'm just saying, this is a consequence of a periodic crystal, so that it must be like this, okay? So now, given that you have a Bloch function state, this is what I'm also saying that you can prove from here in one step or two steps that it should be like this, or if you're given this, you can prove that it must be like this, and vice versa. So it can be related to this physical constraint that the mod psi squared is periodic also. Yeah. Okay. So now what Cornell and Luttinger did is they said that look, I have I don't want to solve the Schrodinger equation for basically in semiconductors. By that time, people have realized you can measure mobilities and effective masses and all that. So they tried to reformulate the theory by and make it closer to something which is much more usable from a perspective of heterostructures and doping and all that sort of thing. And what they said is, let's, instead of looking at individual K states, let's construct states, because an individual K state has it is spread out over the entire crystal. It cannot be located in a small point, near a dopant or inside a quantum well. It's spread out over the whole crystal. It's because its k is delta k is 0. K is precise, right? So, but then if I collect a certain window of k's here and then construct a superposition state of these such that I weight this heavily and weight it a little bit less, weight it less. So I construct a state now which is composed of maybe 4 or 5 different k's, okay, and then I write it as a some phi of x. It's a sum of ck's times psi k of x. These individual Bloch states. I should label it as psi sub k. This is an individual eigenstate of the system. I construct a state which is a superposition of a few k states, few of the eigenstates of the system. And this construction typically would be heavily weighted by the states which are near the band edge, states which you are most interested in looking at, transport of. If you're in silicon, there's, or in silicon, or if you are somehow interested in something which is going on at a higher band here, you just expand around there or wherever you want to, And when you take this, this is still a linear combination of the allowed states. So quantum mechanics and the mathematics underlying it says that this is completely an allowed state of the system. No problem. All these ck's are complex as long as they are complex numbers. It's all fine. And so when you take this, and that's what they do in the paper, they substitute it back there into their equation and make use of the fact that this is actually a Bloch function, right? E to the power I kx ukx, right? This is a Bloch function. And again, when you're summing over k's, you can think of, instead of doing that, you can think of integrals over k space. Again, I don't want to. I'm just pointing out this procedure. I want to use the results, but just want to point this out rather than. Now you can see this starts looking like a Fourier transform of this collection of coefficients. Fourier transform of that. So what you can show that this function will become effectively a Fourier transform of small ck's x times uk of x. This is an approximation. You can show that if your wave packet has a restricted range of k's, under certain reasonable and very physical approximations, it will look something like this. And that's kind of a very interesting thing. Essentially, what you ended up getting is that the total wave function of this wave packet is still modulated by a periodic function, which is repeats every unit cell. But there's also another function here, and this is what's called an envelope function. It depends only on the large scale modulation. It doesn't care about the microscopic details anymore. If you put a quantum well that has 50 lattice atoms, then this will know that there's a quantum well. This one would be unaware. It's more aware of what's happening every 5 angstrom, not in 50 nanometers. So this is the envelope function, and this is the periodic function, lattice periodic function. And what they show, what's really crucial is, it's not very interesting if you just get this. What is very interesting is if you take this now and you plug it, this phi as your solution into the Schrodinger equation, what you get is that the periodic function actually goes away, right? And you get a modified equation. Okay? You get a modified equation, and that modified equation is the effective mass equation. So the mass, which was that of the free electron, that changes to the effective mass of that band. This has to be done per band, meaning if you look at the conduction band, it will be the effective mass of the conductor. If you're in the valence band, it will be the effective mass of the valence band, and so on. And now you are going to have your derivative. I'm going to just write it in a more general case of the envelope function only. No more lattice periodic functions, just the envelope function that remains. And this periodic potential, the periodic potential there, also goes away from the Schrodinger equation. It goes away. Where did it go? It all went into here. This mass parameter captures everything about the periodicity and the strength of the material, of the semiconductor it's sitting in. And your equation becomes, just that is equal to the allowed energy is minus EC, which is the conduction band edge, or in other words, this minimum energy. That's the potential energy. Maybe I should write it this way. Plus EC of R, C of R is equal to allowed energies times C of R. This is your effective mass equation. This one. This is your effective mass equation, which is the modified version of the full Schrodinger equation. And it's an approximation. I'm writing it as equal, but it's an approximation. Yeah, Andrew? Yeah.
So now, if everything about the periodicity of the wave function falls into the effective mass term, does that mean that in a 3D crystal where you've got multiple
directions,
you actually have different effective masses along those directions?
Yeah. So in a 3D crystal, the way I've written here, it looks like a scalar, right? I mean, this term, in a three-dimensional case, if the EK is non-isotropic, if you're going along the x direction and it's curving more, but you're going along y direction curving less, it's a non-isotropic surface. Does that make sense? It's a warped or non-parabolic structure. And in that case, your equation looks slightly different. You will have m star along the xx direction, and then you take your del squared along the x direction. Does that make sense? You take del x, right?
So you just treat the effective mass as almost a vector.
It's a tensor. Yeah, exactly. It's a tensor, so it has some strength, and it also has cross terms. In some more stranger materials, you may get 1 over m star xy, and this is del x and del y, for example. You get all these things too. So you get that. So it's in general a tensor, yeah, okay. We are going to keep this simple, but you know that behind this you may have situations where you may get these non-isotropic situations as well. So yeah. Okay, so this is your new equation, and this is really the effective mass equation that Cornell and Luttinger derived, and they used it to explain quite a few things. Let's look at just flat band situations where the conduction band minima is not changing. It's a bulk material. It's across the structure, and then you can see that I can take, even without that, I can take this E to the right side, and you get E minus EC of R, or E minus EC. That's your new Schrodinger equation. This is the effective mass equation for electrons now. And in structure, it looks exactly like your Schrodinger equation you started with. But the only thing missing is the potential, and that's gone into the mass. Right? So this, does that make sense? And you can see it's definitely much simpler. It makes life much simpler to handle, and that's why it's very popular, and then we are going to use it now. So I think I wrote it here. Now here's why it's so useful. Okay, in addition to being simple, let's say you build a heterostructure like some of the problems you're solving today in your assignment and all that, right? And the heterostructure has obviously a lot of atoms with a periodic lattice, right? So maybe atoms A, and then you go here and you have atom B. That's going periodically again, and then you come back and again A or something like that, right? So that's a heterostructure where the conduction band minimum is doing that. You're going from, say, germanium to silicon, and then the band gap is changing as you go across. This is valence band, this is conduction band, and this is the profile of electron energies now as you go across. So this is a heterostructure. Conduction band minimum here, so in germanium, for example, or a narrow gap semiconductor, this is a wide band gap semiconductor. It has conduction band there and valence band there, right? Does that make sense? Okay. So at all points in real space, this is real space, X or Y. Yeah. So now, if you go to the effective mass equation, meaning the total wave function is clearly, changing in every unit cell. It can have, it's changing in every unit cell. Whereas the effective mass equation is looking only at the envelope part of it. Envelope part is changing slowly, right? Changing slowly. And we know that in this problem, what we will have to do, this is actually the problem you're solving too in the assignment. You have an electron incident, and it's going to come in, and then it's carrying, dragging along with this wave function, both the envelope part and the Bloch periodic part. Now, so the envelope part, if you solve that, that is essentially the problem is as if there are no atoms in the crystal. It's going in vacuum, but it has a different mass. So that makes it very much easier to solve this problem. You can imagine, right? I mean, you don't have to worry about the microscopic details at all. And then if you have a potential barrier like this, which is the minimum of the conduction band changed, then that is a change that will appear here now. It's the additional potential term now. It will appear. Does that make sense? I mean, so any change in the conduction band, so conduction band minimum went from here to there, in which case it will appear as a delta EC here. So this is now your new potential. Right? So you have mapped this problem of a rather complicated problem of many atoms, condensed matter crystal, to the one of the simplest problems in free particle quantum mechanics, which is just that. You have mapped that whole problem to this problem now.
It have a different mass, right?
Yeah, that's a good point. So the only difference is this mass and this mass may be different. Effective masses may be different. So there will be a small tweak to some of the things you might want to do. For example, the continuity equation you use when you use the full wave function is d psi by dx here, coming from the left must be equal to coming from the right. But does that make sense? So x plus is equal to d psi over dx. So this is your continuity equation at any point at x minus, right? But now your psi is composed of two things. This is the envelope function and the Bloch function of the periodic part. So what you can show here is, from this and the fact that the current must be continuous across this interface, really, that your continuity equation must be, m1 times d co, does that make sense? This is the envelope function only. You don't have to worry about the Bloch periodic part. X minus is equal. So effective mass must be taken into account in this, and then this is your modified continuity equation. For example, I will, I'll ask this in maybe the next assignment. You can show it in a couple of steps, but this is how it will change. It's small changes. As long as you account for them, you can still use your free particle picture again. So, yeah. Okay, so you can now use this. So here's really the again looking at and again this part is written up if you want to look further, but the end result is actually very simple in that sense. So for example, you can put a dopant. This potential may not be a step. It can be just a ionized donor. You put that dopant in there, and then it ionizes a charged impurity, and that will look like minus E square by 4 pi epsilon r, which is a Coulomb potential. And when you look at this equation carefully, you realize this is the same equation as the hydrogen atom. You have mapped it to the hydrogen atom. It's a Coulomb potential, which is symmetric, right? And the hydrogen atom is the most solved problem in quantum, where you can find all its energy eigenvalues. So you can find out, if you put a dopant in a semiconductor, what are the allowed energies for that dopant electron, and it will look like a hydrogen atom, except everything will be scaled with the dielectric constant or the effective mass. Because in vacuum, when the electron is going around the hydrogen atom, that mass is the full mass of the electron. And when it's going around a hydrogen atom, the dielectric constant is 1. Epsilon, it's in vacuum. Essentially, there's no matter between. There's nothing between the electron and the proton, right? So it sees it's vacuum. But inside a semiconductor, when you put a donor, it's going around with many lattice constants, and the dielectric constant of the intervening medium is, the dielectric constant of the solid, which is about 10. And the effective mass, as I mentioned, For example, let's say indium gallium arsenide, where effective mass can be about 0.1. So it's 10 times lower mass than a free electron, and this is 10 times higher. And this is the ionization energy of the hydrogen atom electron. That's 13 electron volt, 13.6 electron volts. If your electron is sitting in the ground state of hydrogen atom, how much energy do you need to kick it out into vacuum? Right? So that's 13.6 eV. So you can take 13.6. This is 0.1 of free electron. This is 10 squared. So that's 1 over. So you get 13.6 millielectron volts now. Does that make sense? That's the ionization energy of a donor atom in hydrogen in a semiconductor, for example, and that's very close to what you actually get. So this is the reason that, Cornell and Luttinger really developed this theory to explain some of the experimental observations that we've put dopants, how much energy that is take for you to ionize those carriers from and then in the process they gave us the effective mass theory, which we now use for heterostructures for all these other things. So this is why I just wanted to emphasize that. Yeah, that's a question.
Is that the effective Bohr radius?
Yeah, so this is the ionization energy, and this is kind of the Bohr radius, how far from the electron. So the Bohr radius of a hydrogen atom is what, 0.5 angstrom, right? That's how, something like that, right? That's how far the electron wave function peaks from the center of the nucleus of the proton. But the effective Bohr radius in the semiconductor, if you have electron that's going around a positively charged donor, that will be 10 over 0.1, 100 times 0.5. So that will be 100 times larger than the hydrogen atom, the orbit size. So connected to the donor. So basic message is the effective mass theorem maps the problem of electrons in a periodic potential to the one of the 6 or 7 exactly solved problems you did in your first assignment, either the free electron or a hydrogen atom or something like that. It will map it to that problem. All changes you need to make are, in fact, realize that mass has changed, and that's what is responsible for all the details of the crystal. Okay, so what we'll do now then is use this concept, and whenever I say that I'm drawing an energy band diagram and all that like that, the reality is, in any crystal, in any semiconductor solid or metallic solid, the real potential is much, much more complicated. It's looking, something like this, right? The real complete potential. It's looking something like that for the electron, right? And effective mass theorem is giving you a way to solve this problem without going into all the details of this potential by looking at this effective, smooth potential that goes around like that, right? Yeah. So that's a nice thing. And so let's use this. One of the things I had just about started. So you can see right away that this wave function, or the effective mass wave function, you can write by just drawing of your knowledge from this particle in a box or a picture or the free particle picture, right? And that's what we had just about started in the end of the last class. What we said was the following. I'll just erase these. That I'm trying to push electrons into a waveguide, or a rectangular cross-section area, right? And let's say that rectangular cross-section is not a vacuum, but it's actually a solid that is made of say semiconductor, and it has x, and I keep forgetting. Sorry, x was that. Longitudinal direction was x, and let's call this y and z, right? And then I have so this is my crystal. I've made this out of a block of silicon, for example, and this is Ly, this is Lx, and sorry, Lz, and along this direction is Lx, right? So now I'm going to have electrons incident, and I want to track its quantum transport properties inside this material now, right? And what I'm doing is I actually have this Lz and the Ly to be very narrow, maybe 10 nanometer or something like that, and the electron cannot escape that region. It's going to stay inside. I mean, actually, one of the problems if it has high energies, it's possible to escape. It must have energy higher than the work function and all that. It can go in a vacuum, but let's assume it doesn't have that much energy. Typically, if you make a wire, it will not escape, so it doesn't have that much energy. So when it goes through, I mean, what I was saying is the total wave function will be. I mean, this is just a genesis of how you might be solving such problems in most quantum devices. You can write down the wave function by looking at. Okay, so that's not important at this point. So that you can write it as a product of the XYZ states. So you get in the x direction, it's a free electron. So I write it as e to the power I, kx times x over. I can normalize it as square root of Lx, right? Whatever is the length along the x direction. And it can be a large number, it can be a periodic crystal, whatever, right? I think you can hopefully see right away that this is just a normalization factor, because I take mod this square and I integrate it over x, right? This will give me a 1 always, right? And this will give me a total length. So I'll get a 1 if I integrate dx mod e to the power. Again, this is trivial, but I just want to say that if you think of it this way, it will be very clear that it must be square root of Lx, right? Because when you square it, you will get this, and that is really 1. And for normalization, when you integrate it over the total length, you must get a 1. So Lx over Lx will be 1. So it's a square root of length. And the y and z direction here, it turns out because they are quantum confined particle in a box, there's a square root of 2 here, because it's a sine function or cosine function, sine pi over Ly times integer. Okay, I prefer to write with the integer first, the quantum number ny times pi over Ly times y. So this is your y dependence, and then you get your z dependence, which is very similar, Lz. Right? Times z. Right? So that's your full-blown wave function. But it's not all. There's one more term. Okay, and that term is your periodic potential that takes care of the fact that you are in a crystal. There is this term too, the full wave function, right? But if you are solving the problem in the effective mass picture, which you are free to do if you want to, as long as you take care of the fact that the mass has changed, and whenever you get the mass term, you must replace it with the effective mass, and you must take care of the fact that there's a conduction band edge. Those two parameters completely account for the fact that you are inside a solid. As long as you do that, I don't need to write my psi of x. This part is the envelope function, and I just deal with the envelope function, and I don't bother about that. That's what I'm trying to kind of get to. And I will be dealing with this. And the one situation where it will fail is when you are going to go from one band, electrons will go from one band. Sorry, if I'm going in one band, and somehow I end up in the other band, if I have interband transition, then this will fail. You must account for that, because the Bloch function, the periodic functions are different. So that will fail. But interband tunneling is something we're going to look at in some detail. Yeah, there's a question.
For example, you give the effective mass approximation. That doesn't break down for deep level states, does it?
For deep level states, what happens is you're spatially extremely localized, and you have to go out very far in k-space in your ansatz to build your this effective mass the linear combination. So in principle, the effective mass theorem is exact if you include all k-states. In practice, the utility really comes from the fact that you can get away with a very small range of k-states in the k-space. In principle, if you include the whole block, the whole Brillouin zone, the effective mass theorem is completely exact. There is no approximation whatsoever. Does that make sense? I mean, in that Fourier sum we did, if you include all k-states, then it's an exact sum. You're just solving it in another space. But in practice, the fact that it is very powerful for extended states, where electrons are extended, but limited to maybe 30 nanometer, 50 nanometer, something like that. Does that make sense? I mean, but localized, if you have deep level, typically it's a very localized state. Its extent is 2 or 3 nanometers, or an atomic lattice constant or something. Then, because the delta x is so small, the delta k is very large. So as a result, you must do a lot more work in the effective mass theorem if you want to use it. So that's why it's typically not used. What you use is this, other slightly different, kind of a Green's function approach, which gives much easier solution for finding deep level states, as opposed to effective mass. But if you include a lot of k states, there's no problem. You can find your energies that way too for deep levels. Okay, so this is what we're going to use, and you can see right now from here that if I take, I want to write down the current, quantum expression for the current J, and you can see that actually before I write down the current, let's look at a few other things. Okay, so I want to find what is the velocity of an electron in that state. If you look at the k space, kx is if the physical length is L, Lx, then Kx, and Lx is very large, so Kx is 2 pi over Lx times some integer nx. But if Lx is very large, you can think of it as a quasi-continuous situation, and you have a dispersion along the Kx direction, which is a parabola, and the curvature of this parabola is this effective mass of the conduction band. It's not the free electron mass anymore, so right, and that encodes inside it the fact that it's in a crystal. So these are the allowed states in the kx direction, and the energy, but the total energy is not just that. Total energy has h squared kx squared by twice the effective mass in the conduction band, right? That's the first term. There's also energy because of this and energy because of that, right? But these are particle in a box situation, right? Actually, the expression for energy is exactly the same. This is the allowed k for the y direction motion, right? But it's a standing wave. When you apply your effective mass equation, you're basically just doing del x squared plus del y squared plus del z squared, or d by d2, right? Does that make sense? And whenever I apply d2y by d2 square on sign, it's going to pull out whatever is sitting here twice, right? You get twice of that outside. Then that multiplies by h squared by 2m, and what you get is the y direction will also have its effective energy, but that's a bound state. That's not extended state, right? Over 2m star c. I'm assuming it's an isotropic mass. If it's not isotropic along the y direction, it's slightly different. Then you have to have the y direction mass, and if it's has the tensor property here. But I'm assuming isotropic right now, and same thing for z, right? So that's your total energy of the electron as it will go through, and that captures all the possible energies allowed for the electron inside this quantum y, so all of them. But you see, it's in an interesting way. This is kind of a quasi-continuous way here, but these two are what you will call as the waveguide index in electromagnetism, or the quantum numbers for electrons. I mean, these are the allowed quantum numbers. So ny, comma nz will be, this combination will be allowed doublet of quantum numbers, and each of them can range 1, 2, 3, and so on, not 0. Right? If it's 0, then the wave function goes to 0. It's no particle, right? So does that make sense? I mean, that's hopefully simple. But what does that mean? It means that I have not, if I were to plot the total energies, this is not all the, this doesn't take into account all these possibilities, right? Maybe, so the minimum here, maybe this is because of nx, ny is equal to, say, 1, 1, right? Now maybe I make it 1, 2. I look at the in the z direction it's 2, but in the x direction it's 1. Then I'll have another band like that, right? See that I make 2, 2. I have another band. In fact, if I take 1, 2 or 2, 1, they're two bands, they're degenerate, right? As long as M sus T, these are same, they're degenerate, they're sitting on top of each other. So maybe they're, this thing has degeneracy of 2, this is 1, and so on. Right? So you get all these things, and these are in, will be called as the subbands, and I think you can see why, it's just, is indexed by these lateral transverse quantum modes, it's indexed by that. And at a given kx, you can have an electron moving along the first, n state, or a second subband, or third subband, or some combination of them, and so on. Right. Okay. So, is that clear? So those are the allowed energies for the system. And in addition to the allowed energies, let me just see what else we want to write. So this is 2D. Yeah, this is the 1D. Oh, I can already see a typo. All right. Anyway, yeah, this should be. Anyway, so you can see this is the sketch, okay? Quantum wire. These are some subbands allowed. Here I've chosen Z. So these are this is the envelope function. These are the allowed energies. I've written it in a little more in the tensor form here. And the last thing is kind of the density of states, which is a very important parameter. Oh, so here are the allowed energies. And we generally kind of index this sort of ground state. The combination of these two will be indexed as, you can write it as ny, nz, or sometimes just E sub n. It's a number, so you can index it by, this, and so on. Right, the minimum of that subband. And the density of states, I hope you have also seen earlier. Essentially, it's how many energies are there between, a window of energy. How many states are there in the EK diagram between this energy and slightly higher energy. Right? If you go to the bottom, you can see that in 1D, at least it's clear that you have a bunching of states, and it actually blows up. The density of states goes down. Every time you reach a subband, the density of states goes up very high values, and then it will come down. And you can do the same thing for, by the way, is this clear? I mean, have you seen this density of states picture? Hopefully, I mean, in 1D, for parabolic effective mass, it goes as 1 over square root of energy minus the minimum of that band. So every time you hit a subband, you get a 1 over square root of energy. It blows up initially. It's called this Van Hove singularity, and then you hit the second subband. There's still a tail of the first, and then you hit the second. So so you can see that, yeah, this thing is a little higher than this, and essentially they will all add. The density of states of the first subband is not dead by the time you reach it. It's kind of still going, and the second one comes down. So it's a little higher, and so on. But you get these peaks in the 1D subband. If you go to 2D, quantum wells, this is how a semiconductor heterostructure looks now, right? Now, instead of electron being quantized, before I go there, let me just also try to illustrate a little bit about, let's just wait for a second before you go to 2D. Let's say what I do here is I come in, and in this quantum wire, or nanowire, we put in one slice of a region which has a larger band gap than the rest. This semiconductor layer has larger band gap than this. So as it's moving along, in the conduction band profile, as you go along, it sees a potential that looks something like this now, right? A potential barrier, right? This is EC. As the electron is moving along in the x direction, it sees a potential barrier like that now, right? You can solve the problem again, Okay, so I want to kind of sketch out a little bit about how, in general, you solve it, because I'm going to repeat something that you already have done partly and you're doing in this current assignment. This is the simplest potential profile where you have a step, but you can have any kinds of strange. You can put periodic or aperiodic things. You can put wells and all that. You are solving one now, right, with random potential steps and all that. So here now what you solve is, again, the electron is moving this way, and then you reach this point, and you match, so the k here and the k there will be different, right? Electron k's will be different because your potential energy has changed, the kinetic energy. If your electron is going at this energy, its kinetic energy is all of it here, but here it's only this much, So the k will reduce, so the wavelength will stretch out, right? If when it's this here, and then it'll come back again, right? And then you again do a wave function matching on these two, this side, from coming from here and coming from there, and from here coming from there. So you will write, one is the incident wave, let's say, and you have r e to the power minus I k x, right, as the reflected wave, right? And then on the right side, you can do your transmitted wave t e to the power I k x, right? And inside this barrier, you can do your both transmitted and reflected waves with maybe some a e to the power I k x and b e to the power minus I k x, right? Same deal as any particle in a box or any 1D transport, except now you are taking into account the electron is in a solid with all these periodic crystals, and it's going from, say, gallium arsenide to aluminum gallium arsenide. But the problem has not changed now. Effective mass theorem makes it possible for you to kind of map the whole thing to the same problem again, right? And yeah.
So are you assuming that there's both reflection and transmission on both ends?
Oh, absolutely. Yeah. So I'm saying the electron is incident from the left side, from this side, and I've put a barrier like that, right? And so now I'm taking everything into account, that there will be potentially some reflection, and there'll be some transmission. So I'm not, so transmission is electron gets out from this side, and every other process. So inside here, there'll be some reflection and transmission, and we are looking at a steady state situation when. So when you match these wave functions and their derivatives on the two sides, right, you can get rid of all these 4 coefficients. You get 4 equations. Match the wave functions and their derivatives on 2 sides, so you get 4 equations for 4 unknowns. Solve it, right? And if you want to find your transmission coefficient here, right, or a total transmission probability, right? For this problem, maybe you can. So if your wave vector here is k2. And let's say the total energy, kinetic energy of the electron was E, which is how far above is it here, right? And let's say the barrier height here, is delta EC, which is the potential conduction band offset, right? Then you actually can find that the transmission probability. So you get a very once you take all this stuff and you find out all these 4 coefficients, and you just find t, take mod t squared. The expression you will get is actually, you can do this perhaps in Mathematica. It'll give you a couple of, if you set it up right, it'll just give you the answer analytically. You don't have to do the hard work. So if the energy is E, and if the wave vector here is k, here it's k2, so the answer looks something like this, right? K squared minus k2 squared. I'll just write this down because this will also tell us something about tunneling right now. I just wanted to talk about that. Times sine square, k2 times the thickness d of the potential step. If the potential step here is of a thickness d, that length will appear here. That's your transmission probability for any potential step in one dimension, right? I mean, if it's a uniform height, and this is how it will look, where k is this and k here is this, and this is an exact result. There is no approximation here, and now. So what I'm saying is this is true for a free electron going through, and then you put a barrier in it, not necessarily a solid. But the moment we want to say what is k, what is k2, then the fact that this electron is in a crystal will play a role now. The moment why? Because what is k, right? K is, if I know the energy of the electron E, right? That is what, h square, k square by twice the effective mass in a crystal, right? This is important, right? So this is the effective mass in the crystal plus EC, really. I mean, that's But here, I'm going to assume that, let's say, EC is, well, okay, let's write it this way, plus EC, right? But inside a quantum wire, it's not just plus EC, right? Meaning I shouldn't write it EC, I should write it as E sub n, right? And I have several of those, right? And I have several of those. Let's just look at one for now. I mean, and you can see that different subbands will have different probabilities of going through the barrier, or going transmission or reflecting. So let's just write it as E sub n for all I care at this point, right? This is the energy here. So as a result, okay, so I think I wanted to write it slightly differently. That's fine. Yeah, we can write it. No, is that correct? See, I have drawn this E like this, right? So this is the kinetic energy. So if that's the total energy, I wanted to write it as EC. Forget this arrow. That's not what I meant to write. What I meant to write is that this energy level at which the electron is going is your E. Right? Not. Yeah, I mean, yeah. So this minimum can be anything you want, really. So you can set your minimum here. But now here, so that's K. That gives you that K square should be twice effective mass over h bar squared, and E minus En, right? Right? From here. Similarly, if I go here, now the energy is h squared k2 squared. K2 is the wave vector here, over twice effective mass. Let's assume, there's no need to, but for this case, argument's sake, let's assume the effective mass is same in both regions. It could be different. If it's different, you use the different effective mass here. But let's assume it's the same. We just say m star c plus. You can now see that here I must, if this is if this is En, then this is En plus the potential barrier height. Right? The potential barrier height, which we called as delta EC. Does that make sense? I mean, it's just the change, right? The minimum energy. And so now K2 square is equal to, again, 2 times m star c over h bar squared. Really, I mean, I'm really not doing anything fancy except just writing this down properly. Right? Part of the kinetic energy is taken away by this extra potential energy, so you have less kinetic energy for this one. Right? So and you can take these two now and plug it in here. That's all you really need to solve this problem, transmission problem exactly, and you get an answer, right? So if you take these and plug these in, what you get is the transmission probability is, you can see, 1 over 1 plus. So, let's look at this. K squared minus K2 squared. So that square minus this square, right? And that is, actually pretty easy. That is just 2 m star c over h bar squared. In fact, maybe you can tell me, I don't need to carry this around, because you can see there's a 4th power of k and a 4th power of k. This will just cancel out. It's a constant, right? So it turns out it won't matter, at least in the parameter here. And k square minus this is just delta EC, really. Right? This is just the barrier height. So you get a delta EC, and then you square it here. This minus this whole squared. And in the denominator, you get 4 times, meaning here, you get 4 times this whole business here, and you get over 4. All right, so basically these energy differences, E minus En minus delta EC, right? So this is your term here. And then your sine square thing will now depend on the effective mass very sensitively. And all right, I'm just writing it out, all terms. It's a little messy, but physically I just wanted to see sine squared this times d. So this is your full expression for the transmission probability now. Right? You can plot You can plug in what is the energy of that electron. You can turn the energy, around and find the tunneling probability. It's very interesting now because you can ask, hey, wait, what's going on here? What if my energy is below the barrier height, right? What if the energy is below the barrier height? Does that expression still work? And the answer is yes, that will still work. Actually, there's a question. Sorry. Yeah.
Is the value of En the same for both cases?
Yeah. So I'm looking at just one. This is an important question. I'm looking at only one subband, as I described earlier. And you can do this same thing for every subband. You can deal with them separately. So, for example, if I have the 1-1 or the 2-1 or 2-2, right? Whatever I'm doing, you can do this for each subband separately. If you have electrons in the third subband, you have to do it for the third subband, separately, right? And you have to take the third subband minimum energy. So this tunneling probability will be defined for each subband. Transmission probability for each subband separately.
Electron traveling through the QM where it stays in the same band?
Yeah, so because we're looking at ballistic transport, if I put an electron here, it's not going to jump to another subband, it's going to stay there. If we allow scattering and phonons and all that, it can absorb a phonon and go there, for example, but we will talk about those things later. Right now we are keeping all states independent and orthogonal, not allowing some of these defects and all that scattering. Yeah. Okay, so now if your energy becomes lower than the barrier height, if the energy becomes lower than the barrier height, you can see right away that this term K2 square, there'll be a negative on the right side, right? If this is lower than kind of the combination of these things, then you get a negative. That means K2 becomes imaginary, right? That's right. And that's not a problem because this will take care of this, because sine of I times whatever, right, y, let's say, is I sine hyperbolic. It will become a hyperbolic sine. You can show that in a couple of steps, from Euler relation. So this essentially just becomes hyperbolic sine. And when you turn it upside down, you get the WKB formula, look something like a WKB formula. You get the tunneling probability. So essentially, I'm saying that this, okay, so if energy is below, so Mathematica, for example, will not complain. It knows how to take sine or cosine of an imaginary number. It will just become that, But if there are some functions that will, tools you use that will complain, oh, you're feeding an imaginary number into sine, then you can convert it into a form that will look, it will basically be very similar to this EC squared over, except, there'll be a I squared in the front, so the sign will flip. You get E minus En. Then, this will become positive. Delta EC minus E. So that's how it's become, and it will become a hyperbolic sine squared of this whole quantity, but with the positive sign. I'm just saying it flips around this thing. This has become positive argument. And you'll see that this quantity will be actually pretty large, much larger than 1. I can imagine why, because transmission is very low when you are tunneling. It's not very high. This now is very large, and you can now make this is exact. You can make an approximation and take it all to the numerator, flip it upside down if you might, right? So all these linear terms. More importantly, you get sine hyperbolic square, and sine hyperbolic square, sine hyperbolic has a e to the power plus and an e to the power minus. The plus dominates, and you get minus 2 times. In the end result is you get minus 2 times this whole business here, 2 m star c over h bar squared, this energy differential times d, and this is what is typically given as your WKB result. This is an approximation, and this approximation is actually extremely important. In Kromer's notes that is posted, he derives it, and the approximation says that the tunneling probability by WKB is proportional or very close to e to the power minus 2, an integral of this imaginary, k vector, if you might, imaginary part of it, right? Going from any point, that you are going across in the imaginary k vector, and here it just happens to be the imaginary k vector value is exactly known, and so on. So the same formula takes care whether you are tunneling or whether you're not tunneling. Is the same thing. So you can take care of all that stuff, and you can make a plot of this electron distribution as it comes out, and I think you can know that if your barrier height, if the electron energy is larger than the barrier height, your transmission probability will be very close to 1, but then it's lower, it will exponentially decay. The tunneling probability kind of go down, and this formula will give you both. So, yeah. And what I wanted to kind of use this for is to also highlight that all these processes you are solving in one dimension, at least in the current assignment, but it's the same in multiple dimensions. All that you need to do is take care of the effective mass and the fact that you have subbands or you have some transverse direction, quantum confinement. Other than that, all these are mapped to the 1D problem in the end. So, okay, so what we'll do then is use this to, so that's 2D, bulk materials 1D. You can go to quantum dots, same business. In quantum dots now, you are confined in all 3 directions. The electron cannot move either in X, Y, or Z. You're confined in all 3 directions, and now you're particle in a box in all 3 directions, right? And then your energies has basically you have 3 quantum numbers now because all 3 directions are quantized, right? And now it looks like an atom. I mean, basically your energies allowed are discrete, right? Remember, if you allow the electron to move in any direction, the density of states will spread out because there's a band, right? There's a dispersion. If you don't have a band, the energies will be discrete. So later on, we'll see. Later on, as in maybe 2 weeks or 3 weeks hence now, that you can start with a 2D system, 2-dimensional electron gas system, where the electron is free to move in 2 directions, and you apply a very large magnetic field to it, perpendicular to the 2D electron gas. And the electrons are free to move in this way as you apply magnetic field perpendicular. And classically, that magnetic field, what it does is it wants to electrons to, or charged particles to do circles. So what it does physically is it reduces the degrees of freedom by 2. Right? That's what it does. Perpendicular to itself. If the electron was free to move in 2 directions, it will freeze its directions by 2, right? At a very large field, right? So what will happen is in a 2D electron gas, in a 2D system, forgot to say, but the density of states in a 2D system is a constant for a parabolic band. I think you probably have. So if you, for 1D states, it was kind of peaking and dropping, right? In a 2D system, the density of states as you go from within one subband is a constant. And this is a very important result. And that value is effective mass over pi h bar squared. That's the density of states of any 2D electron system which has a parabolic band structure. Parabolic band structure is an important thing here. It's a constant, right? And so forget about all the subbands. Just one subband, you think of it as parabola. But then you come in now and you apply a very large magnetic field perpendicular to the 2D electron gas, and it will change. Intuitively you can think it's going to reduce the dimensionality by 2. It will go from a 2D system to a 0D system like thing. So it will become, the density of states will become a string of delta functions, if you might, or atomic states, discrete states, and these are called Landau levels. And we are going to look at this because that's the heart of all this quantum Hall effect and all that stuff. We're going to look at that, so. We'll see that this problem, when you apply a large magnetic field to a 2D system, that problem is maps the 2D electron gas system into a harmonic oscillator problem, exactly the same as a harmonic oscillator problem, and these energies will come out to be equally spaced, that you have solved or looked at in the first assignment. So that will where it will end up being. Okay, so yeah, question.
Just backtrack question. How would you measure effective mass experimentally? Yeah. So we will actually discuss about there are various ways. You can actually directly measure, these days you can directly measure the band structure by using angle resolved photoelectron spectroscopy or techniques like that.
And if you know the band structure, you can plot it and fit a parabola and get the mass directly, right? So that's one way, which is now popular. People are using. I mean, it's done here in Duffield, and Professor Kyle Shen's group, they do that regularly. The other is through transport, and this is very nice, because what happens is when you freeze these, when you apply this magnetic field, these Landau levels form, and this separation is related to electron charge times magnetic field divided by the effective mass of the material. So by measuring what is the separation through transport with Shrubnikov-de or integer quantum Hall, you can get the effective mass too. So there are transport ways of doing it. There's a cyclotron resonance measurements which can give you effective mass. If you read Kittel's book, that is described. There are quite a few ways. Okay, so I just want to kind of show one picture of something that experimentally people have calculated from DFT or first principles calculation, just illustrating all these things we mentioned. Here's the red. This material is gallium nitride. There's a little region of indium nitride. Oh, sorry, this is indium nitride, and you have created electron hole state here, for example. And this is the periodic crystal, right? Your atoms are periodic. And here's the full-blown wave function of that quantum state. These wiggly ones are the full-blown wave function. But the dashed line is the envelope function, so we talked about. And the envelope function times a periodic function that is repeating is equal to the total wave function, which is this red one. This is modulated by this is a fully calculated version, and people can experimentally measure some of this too. Experimentally, it's rather difficult to measure at that sort of constants unless you are doing some sort of a tunneling STM sort of measurement. Then you can kind of image it. So, yeah. Okay, so I will use the last few last little time I have to talk about the ballistic transistor now, and I wanted to kind of make sure that you have this under your belts, because this will remain important throughout the course, to be able to, when you look at the problem, it's 1D, 2D, 3D, you should be able to write down the envelope function without, by just looking at the problem. Here's the envelope function that works. And whenever I have a transmission problem, you should be able to treat that problem from this effective mass picture too, right? And use delta EC's effective masses and all that. One more thing I just want to add before I go to the ballistic transistor is that whenever you are solving a problem of transmission and all that, I will strongly suggest also look at what you can intuitively expect from a classical physics situation, because that will always help to guide your answer, always. Because quantum obviously is different, but it's not very different. There are typically so for example, if I think you are solving, we were discussing in the office hours today, if I have a situation where I have some complicated potential, let's say something like this, I'm just arbitrarily drawing this at this point, okay? Here's your potential profile for electrons, and you're saying, well, plot the transmission probability, the full quantum transmission probability of electrons going across this sort of profile, right? So what should it be, right? So classically, what do you expect, right? So if I shoot electrons or particles here, will it make it to the right side? It won't, right? So that should be 0 here. So I'm going to do the classical one first, right? So essentially, first of all, the energies below this are not even allowed. This is the potential minimum. So classically, I'm looking up, and you see all the way till here, my energy transmission probability is actually 0, right? So I get 0, and I go 1, and that's your classical transmission probability, right? And actually, even in semiconductor devices, many times you can go very far by just using this, because in semiconductor devices, if I have a source of a doped semiconductor here, even though this looks like a very high energy, you always have a Fermi-Dirac tail of electrons, always. Right? There's always a tail of electrons, and there's a little bit that can go through. Okay? And in the transistor that we're going to talk about next, this tail is absolutely critical. We are, when you turn off the transistor, you can actually measure this tail directly in the current spectral. When you measure the transistor currents when switching off, you actually measure this. And all the transistor physics is related to moving this tail up and down and all that with voltages. Right? So in quantum mechanics now, what will change? You can see that if the electron energies are slightly over here, then there's a finite probability that it will go through because of tunneling, right? And also above here, sorry, there'll be a little bit of ringing because there's also reflections, right, of waves. There'll be a little bit of ringing, and then it will come down. If in a linear scale, it will look exponential, very sharp, right? It'll come down. In a linear scale, you won't see much features at all. It'll just go down very fast, right? But if you blow it up, maybe draw it in a log scale, go from say 1 to 10 to the power minus 9 or something like that, then you can see the features, right? And it will not look very different. I mean, you can kind of guess it. So it will be kind of high, maybe till here, and there may be some ringing again, depending on the wavelength here. And then suddenly you hit another barrier, so it will drop abruptly again, and so on, right? I mean, you can, hopefully see, and there's a minimum is here. So essentially, every time you increase the total area of this barrier, it will drop drastically again, right?
It'll never be one, right?
What's that?
It'll never be one, right? Even when you go really high.
No, it will go through some ones, meaning over here.
Yeah.
It'll go through some ones. There's always some resonances that will. So I think it will. Look at that. It will. In fact, also in Cromer's handout, look at the single barrier. You will see there are, whenever the wavelength matches, integer. This is a quarter wave sort of picture. There's always a 1 there in the resonance. Yeah. Okay. So, and then use this when you solve the problem. When you solve the problem, see whether it makes sense. Does it have that sort of a feature or not. One important thing is if I'm tunneling through one barrier, okay, I want to point out one more thing here. If you meet a very special criteria, which is the barrier heights of the two are the same, then you will see that there is a very unique situation when the probability will go to 1 again. There's a resonance here. So this is a cavity. It's effectively the same feature. This is a resonant tunneling diode, and if you have this sort of thing, then you can. It's a very weird situation when the resistance due to two barriers is actually smaller for that energy state than the resistance due to one barrier. So that's and this is allowed, and then it's actually used for making resonant tunneling diodes in semiconductor devices. So yeah, Does
the width have to be like 2 to the k value?
Exactly. So these width, meaning these don't matter so much as this width. This is very important, where it's a free electron, meaning where it's not an evanescent state. There it's an important, So it's basically it's exact analog of a Fabry-Perot cavity that you use in lasers, where you have light going back and forth. And it's exact same thing, really. Okay, Okay, so now let's look at the the next topic, which is take this sort of effective mass picture and apply it to the ballistic transistor. So let's erase this spot here. And the transistor we are going to look at will be a two-dimensional system. This problem was solved. The full essentially quantum transport problem of the transistor, field effect transistor specifically, was solved by Natori in 1994 is the paper. If you get a chance, I encourage you to read it. It's because conceptually it's actually a very now that we understand some of these aspects of K-states and waveguide sort of picture, it should make complete sense, So what we'll start with by looking at a transistor is here's how we're going to set the problem up. Instead of looking at a full silicon and all that, we're going to think of a semiconductor which is two-dimensional. It's a sheet. Has some width, okay, and has some width and some length, L, and some W, okay, and the way we are going to set this problem up is say that I have made these two regions. I have populated this semiconductor. And by the way, this was fictitious earlier on, but since discovery of graphene and now all these layered materials, this is very real. You can have a monolayer semiconductor. You can have tri-layer semiconductor, molysulfide or boron nitride, this is very real. You can actually have a 2D sheet now, right, of semiconductor, and then that means it has a certain band structure, right? It has the EK diagram for electrons inside, and it has a gap and some effective mass, and we're going to characterize it by those quantities. These two regions, I'm going to dope it very heavily somehow, and I'm going to populate it with a lot of electrons. These are heavily doped regions. And then I make a contact to it by depositing a metal on it, for example, right? So this is going to be my source contact, and that's going to be my drain contact, just like we have talked about earlier. And these are heavily doped regions. And in this device, what we are always going to do is ground the source always. And the drain, initially in the discussion, we are also going to ground that for now. Also grounded. So that's just a 2D conductor or 2D semiconductor now, right? So I mean, it's a source and a drain. And if I were to draw the energy band diagram of this, or how does the EK diagram look? This is just an illustration, So I'm just going to talk about that. So we are not looking at all these gates yet. We're just looking at 2D conductor cross section, and here's the energy band diagram. It has a gap, and inside it there's an effective mass of conduction band, right? And I have doped these two regions heavily, so I populated the conduction band with quite a bit of electrons, both on the source and the drain. I think you know very well electrons don't have red or green colors, but there's a reason it's shown like that, because once I apply a voltage, those two distributions will do very different things, right? So that's why we've just labeled it like that. And here's the starting point of the picture. So this is the energy band diagram in real space, right? And we are going to kind of focus at one particular point of the device, which is this where the source is going to try to inject these electrons into the channel. This is called a source injection point for obvious reasons. And that's a point where the energy band diagram, it goes from some slope to no slope, zero flat, right? And that point is, if I apply a voltage on the drain and move this, that point will move a little bit, but you will always have a point where the slope is zero, right? Because band is curving that way. So that's the source injection point. And if we focus at that point, we can really solve the ballistic transistor problem in a very nice way, right? So let's first look at the following problem, which to me is actually much more important than the ballistic transport part of it. Qualitatively, let me finish the discussion of how the transistor works from all the ballistic and the quantum picture we have talked about. So this is a 2D electron system. It can, 2D crystal channel, which is in it. There are electrons that are free to move in two directions, right? In the x direction and in the y direction. Right? So you should be able to write down the wave function of that very easily. Free electron in the xy direction, but a bound state in the z direction, for example, is very easy, right? Okay. And then you can find out what are the energies allowed for that electron, right? And the energies allowed for that electron are also, maybe you can tell me, they will depend on kx and ky, right? And let's assume it's isotropic effective mass. So it will be a minimum of the conduction band plus, right? H square by twice mass. And then what do I get? Both, right? Kx squared and ky squared, right? Kx squared plus ky squared. Okay. So those are the allowed energies for the electron in the conduction band. Now, if I look at that point, it's a point in this picture, but really here it's a line, right? It's a source injection point where the band diagram is flat. It's actually a line all across going into the width direction. And initially what I said is I have grounded both the source and the drain, so both are sitting at ground, okay? And the source, you can think of it pretty much as a metal. It's a heavily doped semiconductor. It has a certain Fermi level. It's at the Fermi level of the source, right? That depends on how many electrons you put inside, how much you dope it and all that, but it has a certain Fermi level. And if both of them are grounded, these two are exactly at the same energies, Now, there are, at this potential, now there's a potential barrier for the electron to go from here to there. But then, if I look at that point in the K space, here are all the allowed K points, and all the right-going carriers have come from the source now because it's a ballistic transistor. If they have come from the source, if I populated a K state here, right? So I'm going to just draw that one more time. Kx and Ky, right? So we are saying that, well, we have a allowed, these are all the allowed K states, and we also know that these K states are separated, in the x direction and separated in the y direction by how much? How much is the separation here in the x direction? 2 pi over the L, right? Okay, good. So 2 pi over L. What about this one? Yeah, that's just the width, right? 2 pi over the width, right? This one, yeah. And each of these is, you can again think of it as an electron waveguide mode. Each of these is a mode allowed in the state. It's an allowed state of the eigenstate of the in the 2D crystal, right? That's if I put an electron here in this mode, let's put an electron, let's say here in this mode, what is that electron physically doing? If it is injected into the semiconductor, right? That electron is moving in the x direction, not in the y direction, right? This is on the y, ky is 0. Right? So that electron is moving with a high velocity actually, which is h bar, it's k over mass in that direction, right? Physically. If I put an electron in this mode, that thing is moving with a certain kx and a certain ky. That thing is moving like that. Okay? And then you can see right away that if I distribute, if my source has injected carriers, it will inject carriers that have, a distribution that looks, something like this. It has, injected carriers that are moving in all these angles now. Right? And that's what's shown here, right? And for each of these K points, I think you know all its properties. You know its energy, because that's what's the energy, right? You know its velocity. What is the velocity? It's the groove velocity, which is 1 over h bar gradient of this energy. And that's a fancy of saying just actually what you know right away, that it's h bar kx over mass in the x in the x direction, if you might, plus h bar ky over the mass in the y direction. That's the vector, velocity vector. Right? You can just apply the gradient on these two, and it's very straightforward, really. Right? Okay, so now you can also see that if you have a barrier height like that, very few states would be occupied, because there's a large barrier height. So there's the electrons that are injected, the probability of occupation is very low. The way it's drawn here is as if we have a lot of states occupied, and that is in a transistor done by the third terminal. That's not done by the source and drain. That's done by the gate, which is capacitively coupled through an insulator to this layer. So what the gate will do, as a qualitative summary, is gate is going to control how many of those waveguide states or the quantum states of these are occupied. And so it will control, if you might, the radius of this circle when the drain and source voltages are the same. So it will control, or rather, really the right way to say it is going to control the area of this, because the area is directly related to the density of particles, right? And just to kind of qualitatively, you can write down that the density of electrons is a gate capacitance times the voltage you apply on the qualitatively. And here we'll see there will be a certain threshold voltage that will be necessary to start filling. And this thing will become a parallel connection of two capacitors. One will be a barrier capacitance, the other will be called a quantum capacitance. We're going to see that, maybe today or something like that. We'll see. Okay. So we'll see this is what it's going to become. But then this is also going to be an approximation. This will be only achieved in the on state. In the off state, we'll see it will exponentially decay. And then the full relation between carrier density and the gate voltage is given here. It's a, it's a transcendental equation. It's not a, you have to solve this, carrier density versus gate voltage. So yeah, there was a question.
Yeah. So the gates control. The gates just control how fast electrons are moving, because that's related to the momentum.
Yeah. So the gates will control, rather the gate electrode will control how many K states are occupied, and that is it. If the gate, if the gate voltage is say high, much larger than threshold, then it will, the circle will become bigger, right? Now, all that is saying is I have more states now moving faster, but they're moving in all directions, so the total current is still zero if my circle is symmetric. But it will fill it with more particles, more K states.
And the gates would have to be perpendicular to the longitudinal direction.
So here, that's right. So electrons are moving in the x or xy plane, but the gate is put down in a z direction, meaning, well, I don't know whether I should say that, but the electric field that the gate applies, when you apply a voltage, the electric field that will help it fill or empty these states will be in the z direction, in the perpendicular direction. The field effect is in the z direction.
Okay, but there's two, because you're controlling momentum in two directions, kx and ky. Right?
Yeah. So that's a good question. So nothing changes in the y direction. Everything is symmetric. I'm not. If your gate is parallel to the 2D sheet, then it cannot change anything in the y direction. But sometimes you can also put a gate which is, like a fin, or it turns around. Then you can also affect in the y direction of the device. Whatever we are saying now is everything. I mean, rather, let me put it this way: everything is symmetric in the y direction. Nothing is changing in the y direction. So as a result, all the currents we will have, everything will cancel out in the y direction. The net stuff will only flow in the x here. So.
Okay, but you have a choice over the orientation of your gates.
So in a 2D, meaning I have to think a little bit. So if you are in a 2D system and you want to really control the electron density in this region, then what we are talking about is your gate design that gives you the strongest control is what's called the parallel plate gate, where your gate is a plate that's parallel to the 2D system. Anything else you do will have a weaker gate control. And a transistor is very important to have a very strong gate control. It is actually one of the most important things of the transistor. The gate control should be as electrostatically strong as possible. So, yeah. And the gate is going to then, you had a question? Yeah.
So does the gate potential, so gate to source potential, change the band curvature?
Say that again. The gate to source potential change.
The potential you apply as a gate change the band curvature.
The curvature of the band. Okay, so that's a very good question. The answer is no. The band structure, EK diagram of the semiconductor are not going to change with the gate voltage. So what it will do is it will move the whole thing rigidly up or down, but it won't change the curvatures inside. It will move the whole thing up or down, but it cannot change the curvatures inside.
What about the drain?
Neither one can. None of those can. So these are the non-perturbative sort of approaches. Okay. So now what I want to say is let's physically see why is it. So if I turn on and apply a gate voltage here that is positive, then electrostatically you can see that it's a parallel plate. It's done in a symmetric geometry here, but it's a parallel plate, and a positive voltage on the gate metal means you are taking electrons away from the gate metal, and you're injecting it in the semiconductor. That's what you're doing. And if both source and drain are grounded, you are injecting it from both sides, from the source and the drain equally. And so those electrons really came from the gate and they got injected here. The ones that got in from here are going to the right. The ones that got in from here are going to the left. Right? And by changing the gate voltage, this is just a, there's no net current flowing here, but this is the electrostatic control of the device, which is actually more crucial than the transport part of it. So, and when you calculate how does the total carrier density here depend on the gate voltage, that relation is, that's what I mentioned. This is the relation here. So, right. So you kind of change this carrier density occupation here. Now, if your net current is 0, it's not terribly useful, right? I mean, it's yeah. So, but then you see that there's a lot of current that is going to the right, and there's a lot of current going to the left too, based on these rings here, because the cases. Do I need to sign anything?
No,
okay. Yeah. Thank you. Yeah. Physically, if you want to draw the band diagram with when apply a larger gate voltage, what happens is this band will be rigidly pushed down and the barrier height will go down. And that's why it injects more. Right? And so now, so at this point of time, the net current flowing in a drain is 0. And now you come in and you apply a drain voltage. Okay? You hold your gate voltage at this and you apply a drain voltage now. Right? And when you apply the drain voltage, you can see right away, it's exactly the same as we did for 1D conductor. Now when you apply drain voltage, you pull this down by Q times V. Right? You pull this down by Q times V. Now this distribution function must change now, right? And how will it change? You can right away see that it's harder for the drain to inject carriers to the left now, right? Because the barrier height is larger, right? So, right? And on the other hand, it seems like the source, nothing has changed. It should be able to inject about the same amount of carriers as before, right? Because I only applied the drain bias. But so one of the kind of in a way, the reason for the existence or the usefulness of the transistor is the following. Actually, the source, the amount of carriers it's able to inject will also change. It has to change. And the gain of a transistor, the fact that transistor is really a 3-terminal device which has all these properties of gain and output conductance and all that, saturation of current, comes from the fact that the gate completely controls the area of this curve. That job is not drains. The drain does not control the total area of this. How many particles are there, how many electrons, how many states are occupied. That job is completely the gate's. If the gate loses control, that transistor is not very useful. It's as if you have 3 resistors in series. It's not. It doesn't have. It's a non. It doesn't have gain. But on the other hand, the gate, as long as it completely controls it, so the gate controls the n or the electron density of your transport, and the drain controls the v or the net velocity, if you might. Right? So that's the difference here, and for the area to remain the same, it's very clear that the red right going circle must increase, because the two areas we're saying the gate voltage is constant, and I'm increasing the drain voltage, and you can see right away that this will have a net current for sure, right? And so if you plot the drain current versus the drain voltage, the current will start increasing like a resistor, really, right? And this is completely ballistic, fully quantumic. You can calculate now. All that you need to do is find the velocity of each state. Take a projection along. If you take a projection along y, you can see the current will be always 0 in the y direction because it's symmetric in the y direction, right? But if you take a projection along the x direction, you can see that there's a net current to the right, and if you take a reflection of the green, that circle is going to still give you 0, but you have this ring around it that will give you the non-zero net current. You just sum them, right? So that current will increase, right? And then you crank up your drain even more, right? And at some point, all the carriers are going to the right, right? They've reached this situation now, right? In which case, you apply even more drain voltage. It couldn't inject any more. It's still not able to inject any, right? So all carriers are moving to the right. The area of this is exactly equal to the area of that because the gate is under control. So for a given gate voltage, the current will increase and then it'll just saturate because this current is locked now. It's not changing anymore, right? So this is a very characteristic behavior of a of any transistor really, but in ballistic transistor it becomes easy to see why it will behave in this fashion. And all these carriers came from the source. Right? Now that's not enough for a transistor, but the transistor is really useful because now you can turn the gate voltage, right, and say I want less current, right? And now just let's look at the gate situation. Let's say I'm sitting here at this current, right? And this current is saturated. I say I turn down on my gate voltage now. So gate voltage also is going to shrink this thing, right? And finally it will turn it off completely. And this thing happens exponentially. You know, I mean this well, in a on state it goes linear and then it goes exponential. You know, turns off. So that's on off. And so basically ID versus drain voltage. That's your characteristics. If you look at the drain current log scale as a function of gate voltage, it initially looks like a polynomial, and then it goes down exponentially when the Fermi level really essentially when the Fermi level goes below the conduction band edge here, it goes down exponentially. So this is your on-off switching of a ballistic transistor, and the rest of it is all application of, if you want to. In the assignment, I've actually asked you to calculate this for a realistic two-dimensional material, and you can do this for any semiconductor you want. Silicon, molysulfide, any of these 2D materials. You can do it for graphene if you want. In graphene, it'll come down and go back up again because the gap is 0. So it cannot, it's kind of, there's no gap, so it goes back up again. There's a question? Yeah.
So for this structure, you always have to make sure that your gate is isolated. There's no actual overlap with the source and the drain.
Yeah. So the electrostatics of it is such that you have to be extremely careful that so the hardest part of the transistor is to do what I just mentioned, that the gate should control the electrostatics completely. If you have a long device, it's very easy to do that, when the source drain is long and the gate is very close. But when the gate, distance of the gate to this channel becomes the same, similar to the length of the channel itself, which is in the nanoscale devices, when you have 10 nanometer source to drain distance, you can't put the gate much closer than a few nanometers, right? So then it becomes harder because there's a coupling between the gate and the source and the gate and the drain, and they start interfering with each other's jobs. Drain will apply a voltage, but it will start pulling this down because it's also coupling to the gate, and that is called drain-induced barrier lowering, DIBL, DIBO. So it'll start, So how will it manifest itself? The current, instead of saturating, will kind of, not saturate. It will have an output conductance. That's the word, output conductance. And that's terrible for a transistor, because in a transistor, it's one of these very useful things is beyond, you always operate it in this regime, because now if you have one transistor and you want to drive 4 other transistors with it, right? And it's going to have different loads. Some of these may be on, some of these may be off. So the voltage may kind of flip around a little bit as it operates, goes zeros, ones. And then you want the current to be completely independent of what is loading it. So this saturation is very, very important. In fact, the gain is directly related to the saturation, an amplifier, all these things. So if the current doesn't saturate, if you just see a claim saying that, I have a transistor and they're just showing this linear register changing, that's really not the regime of a transistor which is useful. I mean, it's definitely it has field effect. I mean, with field effect you can do this, but unless it saturates, it doesn't have much value as a electronic device for many situations with RF or digital and all that sort of thing. Okay, so yeah.
What does the Fermi energy look like in the P-type material?
You said in a P-type material?
Yeah, so in the center of the transistor, how is the Fermi energy?
Oh, I see. So in this particular situation, the way it's drawn here, I have the Fermi level is constant everywhere in equilibrium, so it just goes through that, and it's still kind of n-type because Fermi level is closer to conduction band, but it's much less electrons here.
In the case where we apply.
Yeah. Okay. So when we apply you can see. Let me just say this Fermi level. Because it's a non-equilibrium situation, there's current flowing and all that. There's not just one Fermi level, there are multiple. So there is a source Fermi level, there's a drain Fermi level, and there's one, I'm not saying that there's a separate one, but you can define, both of them are affected by the gate. right? So they're all kind of connected. You can calculate what is the net, source Fermi level or the whatever. So you can calculate these things, and the current is also can be related to that as well. So typically the picture is it splits inside, and that split is what carries the current, because if you had the same Fermi level everywhere, there's no reason for current to flow because it already is in equilibrium, right? So there's a bending and split. Okay. So I think we're kind of out of time, but I just wanted to say that if you apply the things we have talked about earlier, like if I want to calculate my electron density in two-dimensional electron density, all you need to really do is sum over all these states, occupation function over all these states. And then if you couple it to the gate, you can find out how this occupation, the total sheet density depends on the gate voltage, and here's the relation. And I will spend some time on Tuesday to talk about this, but I just want to say that this is completely written up and in this set of notes here in this chapter. So it's completely derived, and from what we have done till now, if you read through it, all of this should make just you just use these things, sum over your Fermi functions, integrate it, and you get all these results. And the most important thing about this is really that the device, when it starts operating, has this exponential, switching characteristic. So I'll just kind of look at that. The carrier density controlled by the gate voltage is exponential, and so when the Fermi level goes into the gap, the carrier density goes down exponentially. When it comes into the band, then it kind of bends over. So this is very high carrier density. 10 to the power 13 per centimeter square is the on state. This is the off state. And if you go to lower temperatures, this is basically has a slope of kT by Q, or temperature exponential with temperature. And in linear scale, this is how it looks. It looks like it was off and then it turned on here. Right? In log scale, it looks like that. And the net current, so the carrier density is the sum of the two halves, right? And the current is the difference of the two. Does it make sense? Because that's right going current, this left going current. Right? So when you sum them, find the total carrier density, you take the sum of these two, and the current will be the difference of the two. Right? And that's all to it. I mean, with that you can get all these characteristics. It may take some work to make plots of them, but the formulas and all we can go over in the next time. I've also outlined in the notes also how exactly to go about it. Okay, so I'll kind of stop here with the slides showing that with this formula you can, with this sort of picture you can calculate the transistor characteristic of any material, and all the material properties just do is tell you what's the effective mass, what's the Valley degeneracy, and really that's it. I mean, there's nothing else other than that the material, it's a universal phenomenon is what I'm trying to say, meaning the transistor characteristic, any semiconductor you give me, I can find out the characteristics by saying, all I need to know is what is the effective mass and what's the Valley degeneracy, and if you are making a gate, what is the dielectric constant of that material, capacitive coupling, right? And then you can find out. Okay, so let's finish up today, and we'll continue in the next class, and the assignment can turn in on Thursday. We'll have a little more discussion of the ballistic. Okay.